the thing I wanted to finish up for thermal dark matter is coannihilation. And supersymmetry gives you a good example of this, but it's also important in other contexts. And the idea here is that, remember in supersymmetry with R parity, the lightest superpartner, the LSP, is stable and it's a dark matter. But if I have any heavier superpartner, the heavier superpartners always decay down in a cascade where each step in the decay gives you one superpartner and a standard model partner. So for example, suppose I produce a squark. This will decay into a lighter quark plus another superpartner, which could be the LSP. Or for example, if I have a gluino, the superpartner of the gluon, this could decay into a quark and a squark. And then the squark could decay into a quark chi01. So at each step of the decay, because of R parity, the superpartner has to go to a lighter superpartner plus a standard model particle, or possibly several standard model particles. But the point is that for each superpartner, it decays down in a cascade like this. And similarly, if I have transfer reactions that transfer between superpartners and standard model or back and forth, I have to have either one superpartner on each side, or two superpartners on each side, or two superpartners on one side, and standard model partners on the other, just to make the R parity stuff work out. So one of the things that can happen that can be important is, for example, I could scatter a quark with the LSP, and this could go into a squark and a gluon, for example. So this is one kind of process that can happen. I can have this decay happen in the thermal plasma, yada, yada, yada. And the point is that now my LSP isn't the only guy carrying this R charge. I also have R-odd squarks and other stuff. And I can also have mixed annihilation reactions, like chi01 squark goes to quark gluon. So I can have all kinds of mixed reactions beyond just LSP goes to standard model. And the point of all this is that these extra reactions can also contribute to the final relic density. So the thing we computed previously, our sigma v, for annihilation, corresponded specifically to chi01 goes to some number of standard model particles, and maybe other stuff. But everything on the right-hand side is standard model. But when I have other things that share the stabilizing symmetry, these other reactions can also modify the dark matter density. So coannihilation is essentially taking into account these other reactions. And if I think about two limits, so suppose I forget about all my superpartners except for a squark and the neutralino LSP in a supersymmetric theory. In one limit, suppose my squark, I'll call it case 1. Suppose the squark mass is much, much heavier than the LSP mass. And the LSP mass is the mass of this chi01. In this case, what happens in the plasma is these squarks, first of all, they can undergo their own freeze out. But they can also, after they freeze out, they can also decay down into chi01s. And if this mass is much bigger than this, then effectively my plasma has gotten rid of all of the squarks by the time my LSP freezes out, because this squark has had time to either transfer itself, either to annihilate with the remaining chi01s, or transfer itself by scattering with the gluon into a neutralino LSP, or even just decaying down into the neutralino LSP. So in this case 1, all the density in the squark is transferred to the chi01 before freeze out. And if I transfer density, just a second, if I transfer density to neutralino LSP before freeze out, because it's in equilibrium before freeze out, it doesn't matter. Everything just thermalizes, and I'm still in the same situation as before, and I can compute my thermal freeze out by just including this reaction. Sorry, your question?
So the first scenario is that the squark freezes out from the plasma.
Mm-hmm.
But of course, it continues to have other reactions.
Yes.
And in principle, it can decay down to the LSP and still have interaction with LSP, so that the annihilation happening at a temperature that is different from the plasma.
Oh no! The squark is still in kinetic equilibrium, but the point is, as the temperature falls below its mass, its density falls off the map, and because I can have decays, for example, these decays help keep the neutralino the squark density equal to its thermal density, and all the squark density is transferred into a neutralino density, which then rethermalizes, and everything's at equilibrium. So the point is, because I also have decays and transfer reactions like the reverse reaction here going to here, they're in equilibrium, my squark density can track the equilibrium value. So my squark density falls off the map exponentially as the temperature falls below its mass. And as long as this temperature is a fair bit above the LSP mass, it's going to track the equilibrium very well until freeze out. And by the time the LSP freezes out, the squark density is completely negligible. So in this first case, you don't care about coannihilation. In the second case, though, suppose my squark mass is equal to the LSP mass plus epsilon, where epsilon is something small. In this case, when in this case, when the LSP is freezing out, the equilibrium density of the LSP is going to be similar to the equilibrium density of the squark. And the upshot of that is that, for example, I could have reactions that that could transfer my neutralino density into a squark density, or vice versa. And I could also have this annihilation between the squark density and the neutralino density down to the standard model density. And for example, this would also help get rid of my my superpartner density. And this additional reaction would help things track equilibrium. And so I guess going back to this first case, the relative density of squark to LSP is, in this case, roughly e to the minus their mass difference over the temperature. So as far as freeze-out goes, the thing we care about, the time we start caring about the other density, the squark density during freeze-out, corresponds to when this delta M is similar to the freeze-out temperature of the neutralino LSP. So in this case, too, when these masses are similar, this delta M can be similar to the freeze-out temperature. So in this case, I have to take into account both reactions. And for example, suppose my annihilation of chi01 to standard model is very slow. Let's say I even turn it off. In that case, if I only included this, I would expect a very large relative density, because I wouldn't have very much annihilation. But if this transfer reaction is efficient, or this coannihilation annihilation is efficient, what can happen is that instead of annihilating through itself to standard model, my LSP can annihilate through the squark, which is often more efficient, because this involves a strong interaction. And this would give me a larger effective cross-section than just this alone. So the way to account for this is that instead of just looking at n chi, instead use the total superpartner density. So I define n as a total sum of the densities of all the superpartners. And instead of writing a Boltzmann equation for just the LSP, I write down a Boltzmann equation for this total n density of all the superpartners. So what I get is my master equation, in this case, has a familiar form, dn dt plus 3hn, just like before. But now the collision term is a bit more complicated. The collision term is going to involve annihilation reactions between species I and species j. So for example, if j equals 1, that corresponds to my usual annihilation that we had before. But I could also have annihilations that have species 1 and species 2 going to standard model, and that would correspond to, let's say, 1, 2 here. So my ij corresponds to not just So I equals j equals 1 corresponds to chi1, chi1. I equals 1, j equals 2 would be chi q tilde. And I equals j equals 2 would be squark, squark, goes to standard model, standard model. And then the thing that goes in here is ni and j, minus ni eq and j eq. And I just sum over all the possible mixed reactions as well. So the upshot of all this is that the total Rayleigh density is going to depend on more reactions than just LSP. LSP goes to standard model, standard model. And in the case when you have other particles in your plasma that are close in mass to your LSP, you have to do this more complicated freeze-out calculation. So this is just a very simple generalization of what we had before. Sometimes you don't have to do this full thing. So this is the strictly correct thing. In, for example, this case 1, this thing just reduces to the usual case because the number densities of all the higher components, all the heavier things, just track the equilibrium and become negligible. But in the case where you have degenerate masses, you need to track the whole thing. And this mixed annihilation is called coannihilation. So sometimes it can be very important. Okay, so that's all I wanted to say about thermal freeze-out. The next thing I want to move on to is non-thermal dark matter. And as a specific illustration of non-thermal dark matter, I want to talk about gravitinos. So this is a bit more supersymmetry. Okay, so before, when I spoke about the standard model, every standard model particle has a superpartner. And when we take the standard model and we also add gravity to it, gravity also has a particle associated with it, a spin 2 graviton. And the corresponding superpartner of the spin 2 graviton, when I expand my theory of standard model plus gravity to a supersymmetric theory for everything, I now pick up a superpartner to the graviton particle. That superpartner is called a gravitino. So how do I want to write this? So I have my, so I'll write it this way, with a big G. If I include gravity, I have my spin 2 graviton, and its superpartner is the spin equals 3/2 gravitino. And this gravitino is also neutral. The graviton doesn't carry any electroweak gauge charges. And this is also true for the gravitino. Now, one quirk of, so I've extended supersymmetry to include the standard model, but also gravity. And this combination, you might not be surprised to hear, is called supergravity. And I'm not going to go into supergravity because it's a long topic. But the only thing I want to mention is that, remember, the graviton, even though it's quote-unquote spin equals 2, it's not quite spin equals 2. So if you remember, for graviton, the graviton actually only has 2 independent polarizations. So sometimes we talk about the photon. The photon is quote-unquote spin 1, but it's not quite spin 1. It actually also only has 2 polarizations. So it turns out that for any kind of massless particle whatsoever, there are only 2 independent polarizations, no matter what its quote-unquote spin is. So this is true for the graviton, it's true for the photon, and it turns out it's also true for the gravitino in the limit of exact supersymmetry. So in the limit of exact supersymmetry, the graviton is massless, and so is the gravitino. Their masses have to be equal in the limit of exact supersymmetry. And that means that if I have exact supersymmetry, or in this case, exact supergravity, this means that the gravitino mass, which I'll write as m3/2, is equal to 0. And there are only 2 polarizations, even though we say it's spin 3/2. Now, we know that supersymmetry has to be broken. And when supersymmetry is broken, something kind of funny happens. So supersymmetry is a continuous symmetry. And if you remember back to field theory, whenever you spontaneously break a continuous symmetry, you get a Goldstone boson. Now, supersymmetry is a continuous symmetry, but it has a slight quirk. It turns out that the transformation parameter in supersymmetry is actually fermionic. So this is going to sound a bit cryptic, but the upshot of this is that instead of getting a Goldstone boson from breaking supersymmetry spontaneously, you get a Goldstone fermion called a Goldstino. So if I spontaneously break SUSY, what I get is a massless Goldstino. And the Goldstino has spin 1/2. Okay, so stepping back, if I think about gravity and general relativity, one way to think about general relativity is I take the global symmetry of flat spacetime, and those global symmetries of flat spacetime are the Poincare symmetries of translations and boosted rotations. And I elevate those global symmetries to a larger group of symmetries that is invariant under local coordinate transformations. And when I do that, I get general relativity. And in this sense, you can think of general relativity as being a gauging of the Poincare group. Now, the picture of supergravity can be done similarly. In the case of supergravity, you can think of supersymmetry as this generalization of the Poincare symmetries, as a generalization as a global symmetry. But if I take that global supersymmetry theory and I extend it to a local symmetry, it turns out that I get supergravity with regular general relativity as a subgroup. And when I get supergravity, it's now a local symmetry in the same sense that gauge theories are a local symmetry. And if you remember what happens in gauge theories, if I take a global symmetry and spontaneously break it, I get a massless Goldstone boson. When I take a continuous gauge symmetry and I spontaneously broke it, the particle that would be the massless Goldstone boson gets eaten to make the vector boson massive. So when I spontaneously break the local symmetry of supergravity, what happens is my Goldstino, which would be massless, if I were looking at global supersymmetry, this massless Goldstino gets eaten, and the thing that eats it is the gravitino. So what ends up happening is my Goldstino is eaten by the gravitino to make a massive spin 3/2 particle. And now the corresponding mass, I write it as n3/2, not equals to 0. And if I count degrees of freedom, remember my massless gravitino had 2 polarizations, as I said before. And my massless Goldstino is a spin 1/2, so it has 2 spin states. And when I plunk those things together, the degrees of freedom work out because my massive gravitino now generally has spin equals 3/2. And spin 3/2 has 4 different, if you like, magnetic substates. I have minus 3/2, minus 1/2, 1/2, 3/2. And my massive gravitino in this case has 4 polarizations, which is what you would expect for a massive spin 3/2 particle. Okay, so everything works out, and this whole story is completely analogous to the spontaneous breakdown of a gauge symmetry. The only difference is that my scalar Goldstone boson is now a fermion Goldstino, and that fermion Goldstino is eaten by the fermionic gravitino to make a massive gravitino with mass n3/2. So this gravitino is the object. This massive gravitino is the object I want to talk about as a candidate for dark matter. So the first thing I have to tell you is how the gravitino mass compares to the soft mass. So remember, the standard model superpartners have a mass set by the scale of soft supersymmetry breaking. So I need to compare the gravitino mass to that, And I also have to tell you how the gravitino couples to the standard model and its superpartners. The other thing is, as before, if I have R parity in my theory, my graviton is R even, and my gravitino is R odd. So for example, if the gravitino is the LSP, it could be a potential dark matter candidate. So this is where the gravitino story comes in for dark matter. So here, I'm just going to parameterize this. So it turns out that in theories of spontaneous breakdown of supersymmetry, the way we parameterize the result is as some dimensionless coefficient times a combination of two parameters. So the thing in the numerator is this F term is the scale of supersymmetry breaking. So this F parameter has mass dimension 2, and it's analogous to the VEV of a Higgs that would spontaneously break a gauge theory. And so this is the first step. Where the actual supersymmetry breaking happens is characterized by this F parameter. It has mass dimension 2. This thing in the denominator is a mass scale of physics that communicates supersymmetry breaking to the standard model. So the big picture here is that it turns out that we typically break supersymmetry in some sector that's different from the standard model. So the picture to have is that we have the standard model plus all its superpartners over here. And we make sure that supersymmetry breaking is off hidden in some other sector. It turns out that really bad stuff happens if I try to break supersymmetry directly within the standard model. And once I've broken supersymmetry, the supersymmetry breaking is characterized by this F parameter. The assumption is that the supersymmetry breaking, parameterized by F, is communicated to the standard model by some mediator physics with a characteristic mass of m star. And when I put all this together and turn the crank, the generic prediction I get is my soft masses are some dimensionless coefficient times F, which is the scale of supersymmetry breaking, divided by the mass of the mediator. Yes? Yes. Yeah. So this F has mass dimension 2, and this denominator has mass dimension 1. So the whole thing has mass dimensions of 1, as you expect for a mass. So this picture is sensible in the sense that my soft masses go to 0 if I turn off supersymmetry breaking, if I set F to 0. And my soft masses are also suppressed if the physics that communicates the supersymmetry breaking to the standard model is very heavy. The heavier the mediation, the weaker the communication. So this is the story for msoft. And there are different specific theories of how supersymmetry breaking and mediation happens. And they have various names. So this is the story for msoft. For the gravitino, though, the mediation always goes through gravity. So it turns out that m3 halves is always given by F over root 3 m Planck, where m Planck is the Planck mass. And I'm always, in this class, I'm always going to use a reduced Planck mass of 2.4 times 10 to the 18 GeV. Sometimes people write the non-reduced Planck mass, which is about 1.2 times 10 to the 19. And the only difference is a factor of root 8 pi. So this is your m3 halves. And it always depends on F over m Planck. Depending on the details of supersymmetry breaking communication, I'll have different values for C star and m star. So let me just give you 3 popular examples. The first popular example is gravity mediation. And in gravity mediation, I have C star of about 1, m star equal to m Planck. So in gravity mediation, this implies that m3 halves is roughly the same size as msoft. There's something called gauge mediation. And in gauge mediation, I have C star of about 10 to the minus 3. And I have m star much, much less than m Planck. And the upshot of this is that I typically get m3 halves much, much less than msoft. So in this case, in gravity mediation, I expect the gravitino to be my LSP. And finally, there's something called anomaly mediation. And in anomaly mediation, I have C star of about, I have a C star of about, again, roughly 10 to the minus 3. I have M star equal to M Planck. And the upshot of this is that now my M3 halves is much, much bigger than M soft. So depending on your underlying theory of supersymmetry breaking and its mediation, I can have these different cases of a heavy gravitino, a light gravitino, or gravitino that's about the same in mass as a regular standard model partners. And then you can have variations or mixtures of these in which the C star varies and M star varies. And so for our purposes, we'll just treat the gravitino mass as a free parameter. Something can be less than M soft or larger than M soft, and it's an underlying theory question. Okay, so this is the first thing. This is the gravitino mass. The second step is I need to tell you about how the gravitino couples to the standard model and its superpartners. And here, let me just write down the effective Lagrangian. The effective Lagrangian involves higher dimensional operators suppressed by the reduced Planck mass. And there's a coupling that couples the couple standard model fermions and fermions to the massive gravitino particle. So the field I'm going to use to describe the gravitino is going to be a fermion with a Lorentz index on it. So the combination of a fermion with a Lorentz index gives me enough independent degrees of freedom to make a massive spin 3 halves gravitino. So here I have a gravitino coupling to a standard model particle and its superpartner. And then there's also a coupling to gauge bosons. And the coupling to gauge bosons goes like, again, 1 over M Planck. And then here I've got my gravitino coupling, psi mu. And then I have some Lorentz structure. And then I have a gaugino field. And then I have a field strength for the gauge boson. And then I need to add the Hermitian conjugate. So this is a field strength, del nu a rho minus del rho a nu, just a regular vector boson field strength. And this is the gaugino for that vector boson. Okay, so the story is that the coupling of my gravitino is always to standard model particle superpartner with a 1 over M Planck strength. And similarly for the gauge bosons. Standard model particle superpartner gravitino with 1 over M Planck strength. Okay, now there's one twist to this. And the one twist to this is that depending on the relative masses of the particles and the relative energy of the processes, sometimes the effective strength of the interaction is actually a lot stronger than 1 over M Planck. So the way to estimate these processes, well, you can estimate these processes pretty well using dimensional analysis. And for example, suppose my gravitino was very heavy compared to the standard model particles and their superpartners. Yes, Stephen?
The gaugino that you wrote down, is that the photon or is this some of it?
It's any gaugino of the standard model.
Okay,
So it could be U1, SU2, or SU3.
So if it's SU3, then there would be like extra terms in the
Yes, yes. Possibly, yes. Okay, so for example, I could take this and I could estimate the gravitino decay rate. And for M3 halves, much bigger than M soft, I could estimate the gravitino decay rate just by dimensional analysis. So the decay width, or the decay rate of the gravitino, so I'll write this as M3 halves. If I was to take this interaction and compute psi goes to f tilde f, I know that because of this M Planck, I need to have in the amplitude, well, 1 power of m Planck. So when I take the squared amplitude to make the matrix element, I get 2 powers. But the whole quantity, the decay width here, has dimensions of mass. So I need to get the dimensions right. So to get the dimensions right, I need to go back and figure out what my energy scale of the process is. And the energy scale of this decay is set by the largest mass in the problem, which is the m3 halves, which I'm assuming is much larger than the m soft. So for the decay of psi nu goes to f tilde star. The only other mass scale I can put in here to make up the dimensions is m3 halves, and I need 3 powers of that. And then there's usually a 1 over 4 pi just for phase space. So my dimensional analysis for the gravitino decay rate in this limit where it's very large compared to m soft is m3 halves squared over m Planck squared, with maybe a 1 over m pi. And it turns out that this is basically correct up to order 1 numbers. But something slightly weird happens in the limit when the energy scale of the process is much larger than m3 halves. So let me, okay, I'll just go over here. So this is going to be important for us. When the energy scale of the process is much larger than m3 halves, and a nice example of this is suppose I look at the limit where m soft is much bigger than m3 halves. In this case, I would be computing the decay of my superpartner into a standard model particle plus the gravitino. In this case, something slightly funny happens. So naively, you would expect the decay width, so m3 halves, and I'll put naive here because this is what you naively expect. You'd expect this to go like, I got my 1 over 4 pi. I would expect to have a 1 over m Planck squared in the denominator, and then I would expect everything else to be made up by the largest mass scale in the problem, mf tilde cubed. It turns out that this is not quite right. And it's not quite right for a slightly subtle reason. And the slightly subtle reason is that when I compute with the gravitino, I have to do polarization sums. So if you remember doing polarization sums with a massive vector, when you do the polarization sums, gives you a factor of minus eta mu nu plus p mu p nu over the vector mass squared. And in the case of a massive vector, suppose the energy of my process is very large compared to the vector mass, then this term would give me a piece that would have essentially momentum squared over mv squared, and it would give me an enhancement that looks something like e squared mv squared enhancement. So it turns out that with the massive graviton, you actually get something similar to that. So for the massive graviton, there's actually a similar enhancement relative to this. So this isn't quite right. The way to deal with the enhancement is to realize that at high energies, at energies that are very large compared to the gravitino mass, the massive gravitino acts effectively like the underlying Goldstino. So for energies much larger than m3 halves, psi mu, my massive gravitino acts like a massless gravitino, sorry, a massless Goldstino. So the way to get the way to deal with this is to replace my psi nu by a root 2/3 del mu of psi times 1 over m3 halves. So here the dimensions work out. This psi is my Goldstino. And what ends up happening is when I plug this into my interaction, I get an effective interaction where I replace the 1 over m Planck by well, I replace the 1 over m Planck by I get an extra derivative, and I get an m3 halves down here. And if you put everything together, m3 halves times m Planck is roughly f. So the effective Goldstein coupling picks up, instead of a 1 over m Planck, instead I get an extra derivative and a 1 over f. And this 1 over f coupling is what you expect typically for Goldstone type couplings. The strength of Goldstone couplings to stuff goes like 1 over the energy scale of spontaneous breaking. So the upshot of this is that when I plug in this replacement at energies much larger than m3 halves, and this is an example of energies much larger than m3 halves, what I find for the correct actually, sorry, I don't know what I wrote here. The correct decay width for f tilde goes to psi mu f. In this case, I still have my 1 over 4 pi. But now, instead of having a 1 over m Planck, I do this replacement. And this replacement means that in my denominator, I get an extra m3 halves on top of the m Planck. And I get that in the amplitude, so I have to square it. And then to make up the dimensions, I have to put in however many powers that are needed to get the dimensions right. And the dimensional quantity that goes in here corresponds to the largest energy scale in the problem. This would turn out to be m f tilde to the 5th. So it turns out that the decay width for a superpartner going into a lighter gravitino in a standard model partner actually gets enhanced. So I can rewrite this result as my naive result plus an enhancement factor. So I still have a 1 over m Planck squared here. And I have my m f tilde cubed over m Planck squared. But I also have an enhancement factor by mf tilde over m3 halves squared. So the extra enhancement can be understood in analogy to what happens with a massive vector boson. Remember, for a massive vector boson, I get this E squared over mv squared enhancement. What's going on here is essentially completely analogous. I get this enhancement by the energy scale of the problem divided by the mass of this funny object, simply from the polarization sum of the massive graviton. So I'm mentioning this in passing, but the point is that my superpartner decays to gravitons can actually be enhanced. So now let me take the story and put it all together and try to fit it into dark matter. So now that we have this whole story of gravitons, or gravitinos, depending on how my supersymmetry breaking works and what my F scale is, I can have a lot of different possibilities for dark matter beyond just a neutrino LSP in the supersymmetric extension of the standard model. So let's start off with the case of gravitino as dark matter. So this is the first case. And this corresponds to m3 halves less than or similar to m soft. So in this case, you can make the dark matter in a few different ways. But first of all, in the case when m3 halves is much less than m soft, we're in this first limit where the effective couplings go like 1 over m Planck. Sorry, at least to the gravitino to itself at low energies. So in this case, it turns out that the interaction ends up being very weak between the plasma and gravitinos. And you end up getting a thermal Rauch density. It's just omega gravitino, 3 halves. It's roughly 0.1 times m3 halves over 100 electron volts. So the story here for thermal dark matter is that you can show that okay, so the case for thermal dark matter is that suppose I want to start with a plasma where the gravitino was once in thermal equilibrium. If I start with a plasma where the gravitino was once in thermal equilibrium, you can show that its interactions are always so weak that it froze out while it was still relativistic. So when I was talking about freeze out previously, I concentrated on the case where the freeze out was non-relativistic. But if you take a particle that interacts very, very weakly, it might freeze out while it's still relativistic. And that's what happens for the gravitino. And the resulting relic density you get is actually, to get the right relic density, I need to have a very, very light gravitino. And it turns out that a very light gravitino is a problem because a very light gravitino is not necessarily non-relativistic. And you can show that this is actually ruled out because the dark matter would be not non-relativistic enough. And you can show that having very light particles like this is basically completely ruled out unless the gravitino mass is less than about 10 electron volts. So the upshot of that is that thermal gravitino dark matter doesn't work because it would be either too warm or I wouldn't get enough relic density. Yes?
The gravitino does interact with other particles. It does only interact with the weak interaction and the gravitational waves.
Well, its interactions are all given by those things there.
So it's like a weak.
So it's like weak where I replace the W mass by M Planck. So it's sort of really, really weak.
Right.
Okay, but okay. So anyway, to make a long story short, thermal gravitino dark matter doesn't work. To get the right relic density, I need a mass that's so light that it's not cold enough to be dark matter. It would end up washing out. It would end up washing out structure that gives you galaxies and so on. So that's no good. On the other hand, okay, well, sorry, I have this, but I also have a problem. And that problem is that if my gravitino ever thermalized, and the gravitino, suppose, was heavier than 100 eV, I would get way too much dark matter from it. So the second implication is that gravitino must never thermalize unless it's really, really light. So the condition to thermalizing, it turns out that for the gravitino to thermalize, you need a really high temperature because it interacts very weakly. You'll see in the tutorial today that the stuff that interacts through these higher dimensional operators, these operators suppressed by heavy mass scales, require very, very high temperatures to thermalize. And this translates into an upper bound, assuming I have a gravitino that's not lighter than 10 eV. This gives me an upper bound on what's called the reheating temperature. So the reheating temperature, the story for the reheating temperature is that we think we had inflation. And during inflation, all the radiation density was completely diluted, and the temperature essentially went to 0. But after inflation happens, whatever drove inflation, let's say the inflaton field, decayed, and it decayed into standard model partners with a lot of energy. And essentially, all the energy from the inflaton field then went back into making a thermal bath of standard model particles. And at some point, you transition over from a universe that's dominated by the inflaton field to a universe that's dominated by radiation. And the temperature of the universe when that transition happens, it corresponds to the largest temperature of the universe while it was radiation dominated, is called T reheat. So you can think of reheating temperature as the largest temperature of the universe, specifically while it was radiation dominated. So the point is that to avoid thermalizing this gravitino and giving it too large of a relic density, I end up getting an upper bound on the reheating temperature that depends on essentially the gravitino mass, assuming the gravitino is heavier than 10 eV. So that's the first thing. So from this point of view, the gravitino is actually a bit of a problem. It's not very good at making dark matter for me. But even beyond that, I get a limit on I get a limit on how much I can produce of it from I get a limit on how much of it I can produce from reheating, and this gives me an upper bound on reheating. Okay, so the thermal story for dark matter isn't so good, but it turns out there's a nice non-thermal story. And the non-thermal story well, there are various aspects to it, but let me give you one of them. Remember that in this limit, my soft mass, my MSSM superpartners, are going to be heavier than the gravitino. And above here, I estimated my decay rate for a standard model superpartner to decay to the gravitino. In this case, my standard model superpartner, at least the lightest one, is no longer the LSP. It's actually it's because it's heavier than the gravitino. So instead we call it the NLSP, the next to lightest supersymmetric particle. So in this case, my lightest standard model superpartner is going to decay into the gravitino plus something else. And based on our estimate here, the rate for this is 1 over 4 pi, the mass of the particle to the 5th over m3 halves squared and Planck squared. Okay, so it's not quite equal. It's sort of a squiggly because there's an order 1 number. But the upshot of all this is that if I look at this decay rate and I compare this decay rate to when this decay would happen in the early universe, it turns out that this decay typically happens. This decay happens after thermal freeze-out of the NLSP, assuming an NLSP mass of about 100 GeV, if the gravitino mass is larger than 100 keV. So suppose my NLSP, my lightest standard model superpartner, so I'll call this M chi, is about 100 GeV. From this, you can show that M3 halves greater than about 100 keV implies this decay happens after freeze-out. So the picture is this. I have my usual supersymmetrized standard model, and I have the usual freeze-out dynamics in the standard model, in the supersymmetrized standard model. So here, my lightest standard model superpartner has some relic density at the end of the day. But after it freezes out, the standard model density, the standard model superpartner density hangs around for a bit. But then at some later point, it decays into the gravitino. And this is going to create a relic density of gravitinos from the initial freeze-out of the NLSP. And the final density of gravitinos you get this way is a contribution to the gravitino relic density. And the contribution to the gravitino relic density from this decay of the NLSP is going to be just M3 halves divided by the NLSP mass times omega h squared that the NLSP would have. So what I mean by this is each of these NLSP decays, so I'm going to call my NLSP chi. Each of these NLSP decays produces 1 gravitino and some standard model stuff. So that means that the number densities of the gravitino is going to match up to the number density of the NLSP before it decayed. But the contribution to the relic density, remember, is number density times mass. So because the gravitino is lighter than the NLSP, the chi, I get this factor. And this omega chi h squared is the relic density that chi would have if it were stable. So the story here is that I have a usual freeze-out. this usual freeze-out creates gravitinos. And the gravitino relic density, the contribution from this, is just given by what you would compute from thermal freeze-out, but with a scaling factor. And sometimes this scenario is called super WIMP, dark matter. And it could potentially work if, let's say, this is a bit too big, but the gravitino mass is a bit lighter than the NLSP mass. Everything works out. Now, there's also a problem with this, though. And the problem with this is that when these masses aren't too different and you get about the right value, it turns out that these decays happen just after the start of nucleosynthesis. So nucleosynthesis is a period in the early universe where you go from free protons and neutrons, and they come together and form light elements. And you can compare the predictions from nucleosynthesis to the light element abundances you actually measure in the universe. And the predictions match very well with the observations. So this means that if there are new processes that mess up those light element abundances, you're in trouble, because this would change the prediction versus observation. So it turns out that the super WIMP scenario is actually in trouble because these NLSP decays also produce energetic standard model particles. And the energetic standard model particles could destroy some of the light elements created in nucleosynthesis. So this scenario is not necessarily ruled out, but it is constrained by nucleosynthesis. OK, so this is one possible contribution to the gravitino mass in this situation. Now, there's another case. And the second case is if M3 halves is less than about 100 keV, the NLSP decays into gravitinos before freeze-out. And it turns out that this decay before freeze-out, because remember, before freeze-out, your density is much larger than the density at freeze-out. Typically, if this decay happens before freeze-out, you get too much gravitino relic density from gravitinos if the standard model superpartners were thermalized. So this case is also bad. So the limit for being less for gravitino masses below 100 keV is that you even have to make sure that not only the gravitinos didn't thermalize, you also have to make sure that the standard model superpartners didn't thermalize either, because otherwise you get too much dark matter. So that's not great. Now, there's one additional contribution to the gravitino density that is still technically non-thermal, and that is that even if I don't have thermalized gravitinos, so thermalized gravitinos would mean that the thermal interactions and scatterings would create enough gravitinos that the gravitino density would match the thermal abundance you'd expect. But even if I never get to the thermal abundance, I can still have some production in the forward direction. So in other words, if I write my Boltzmann equation for the gravitino density, my Boltzmann equation for the gravitino density, if this density is less than the equilibrium density, then reactions are going to push the forward reaction to create more gravitinos, even if I never actually get to equilibrium. So what happens in this case, it turns out that I can have processes in the plasma like this. I can have a gluino scatter with a gluon to make a gluon and a gravitino, for example. And I can have other processes like this. And these reactions can create a gravitino density that is still less than the equilibrium density, but is non-zero. So it turns out that the contribution to the gravitino density from this kind of scattering reaction is roughly 0.1, which is the right amount, for a gravitino mass of about 100 keV. it depends on the gluino mass. And this corresponds to a reheating temperature of about 2 TeV. So the point is I can get a density of gravitinos from this forward reaction. This is still less than the thermal abundance. I never quite reach the equilibrium, but I'm being driven towards equilibrium by let's say, gluon scattering. And the density I get is proportional to the reheating temperature. So depending on what the gravitino mass is, I could have a gravitino mass of, let's say, 100 GeV, in which case I could have a much higher reheating temperature. Yes?
So is that mg tilde in the gluino mass, the second factor, the third factor?
Oh, yeah, sorry. So this is the gluino mass.
What M3?
So
why are you calling it M3?
Because the gluino, so this is the gluino. The gluino is the gravitino, sorry, the gluino is the gaugino for SU3. So people often write the gluino mass as M3 instead of M gluino. Sorry about that. OK. So all these limits, I can put them together. And I can write down an upper limit on the reheating temperature, assuming I have gravitinos, that depends on the gravitino mass. So I need more blackboard. Let me try.
There's one behind.
Yeah. Perfect. So the total net result is I can write a limit on T reheat. So down here I have 10 EV. Here I have something like 100 kV. And then here I have something like 100 GeV. So along this axis I have M3 halves. And I have an upper limit on the reheating temperature. So this is the reheating temperature in GeV. And so first of all, if my gravitino mass is below 10 eV, I don't care. Gravitino mass below 10 eV doesn't really matter. But for larger masses, out to about 100 keV, I have to make sure I don't thermalize the standard model superpartners. And to avoid thermalizing the standard model superpartners, I can't reheat to above about 100 GeV. As I go larger than 100 keV, I can start reheating more and more. But I do have to make sure that I don't overproduce the gravitino dark matter from this process. And that means that I get a turnover, and then I have some increasing function. So the point is that I have to live below this line, but that if I live at least over here on the border, I get the right gravitino dark matter density. So the point is that gravitinos can be dark matter, but they have to be non-thermal dark matter. And gravitinos are just one example of non-thermal dark matter. But they give you, through these various mechanisms, they can give you the right relative density, or they can cause problems if you reheat it too much. So there's an interesting interplay between the structure of your supersymmetry breaking and your structure of your inflation theory and how much you heat after inflation. OK, so I'm going to wrap it up there. I'll talk about a few other non-thermal mechanisms in the next class. And then from there, I'm going to move on to ways to actually detect dark matter that don't use its gravitational interactions. So I'll start talking about how to measure dark matter and how to look for theories of dark matter in experiments. So wrap it up there. And oh, yes?
So can I just clarify if this is from back before in your Lagrangian at the top?
Yes.
The second term, is there's like a re-index mu? Is that supposed to be contracted over something?
Oh, yeah. Actually, let me just see what I. Yeah, that should definitely be contracted. OK, I have a typo. I think there's another gamma mu in the vertex. Let me check that and. OK, I think there should be a gamma mu here. But I'll check that and fix it in my notes. Because right now I have a typo in my notes. And yeah, you're right. I did forget a factor. Anything else? No. Okay. And I guess you have a tutorial with Jibra, and in the tutorial you'll discuss some of estimating cross sections based on dimensional analysis, and also estimating when things are in equilibrium or not. Again, based on dimensional analysis, which is a really handy skill to have.